Hello everyone. Today we are talking about low-rank modeling of third-order tensors. First, we introduce what is low-rank modeling. Please look at those pictures. As is well known, in MATLAB, those images in MATLAB are stored as a matrix. You can see for this kind of images, has global symmetry. You can see, for example, this Chinese character, it is very symmetric. And of course, the human face is also symmetric. And this picture, so you can see this picture in the building of Department of Math. This picture is very symmetric. You can see this column is identical to this column and this column. So that means what? That means if we store those images in MATLAB, the matrix represent those images are low rank matrices. What I mean low rank is that the rank is much smaller than the number of columns. So our purpose of research is to pursue such kind of low-rank structure in high-dimensional dataset. For example, in this image, you can see in this image there are lots of spots. Those spots are noise, and these noise are sparse. Sparse means that if we use matrix to represent this image, so this matrix has lots of zero. And the background, you can see this background, the columns are highly correlated. That means this background image is a low rank matrix. To separate the low rank and sparse parts of an image is called robust principal component analysis. This kind of technique to recover the low-rank structure of an image was introduced by Cadiz, Ma Yi, Zhuan White in 2009. So this is a truly breakthrough in computer vision. For example, this is a very typical application of robust PCA. So this is a video sequence. You know that, for example, in the mall or some other places, there might be some cameras. The camera record, record what happened in the building. So for example, in this image, you can see the background store or some other stuff cannot change, but there are lots of people moving around. Those people are always changing. That means the background is a low rank matrix, and those people moving around are sparse error in this image. So for each time, we have an image, and this image has height and width, and we can transfer this image into a single column in a big matrix D. For example, here we have 200 frames. So we have a big matrix D. And if we do robust PCA on this matrix, we can separate the low rank approximation of this video D and a sparse error. And a sparse error. So this is another application of long-range structure, which is called subspace clustering. This kind of technique works better in high-dimensional data. For example, this is different from the traditional k-means clustering. The k-means clustering is to separate a data set into k clusters, and points in the same cluster are very similar. Points in different clusters are very different. However, subspace clustering is to make use of the geometry of the data set and cluster those data into different subspaces. Okay, but you can see those pictures in MATLAB. Those pictures are stored as matrix. For example, this image, this part of the image is a part of a matrix, and each element of the matrix represents a pixel in the image. This is true for a gray level image, But for video sequence, you can see for video sequence, each time we have an image. So it is not very natural to transfer this video sequence into a matrix. We can do this, but it's not sufficient, and it will lose information. So it's better to treat this video sequence as a three-dimensional matrix, which is a cube that is also called a tensor. For example, for this color image, the color image has 3 channels, 3 RGB channel, That means this is a cube. This is not a matrix. This is actually a cube, For example, this image, we can store this color image in MATLAB as 3 matrices, 3 matrices. And this matrix, those 3 matrices can be stored as a tensor. A tensor with 3 slices. And for this facial image, because it has several features with expressions. For example, one feature is expressions, one feature is people, one feature is illuminations, and one feature is views. So it's better to store this facial data, facial image data as a 3-dimensional tensor or even 4-dimensional tensor. In one sentence, as dimension become bigger, so it is not sufficient to use matrix to deal with those data sets. So we introduce tensor. So people have studied tensor for more than 100 years. And at first, people used mathematical tools to study theoretical aspects of tensor. For example, multilinear algebra, algebraic geometry, and high-dimensional statistics. And recently, people studied non-convex, convex optimization algorithms for tensor decompositions. In recent years, people in computer science focus on application of tensors in computer vision, image processing, and some other stuff, A recent breakthrough in theoretical tensor research is the introduction of tensor PCA, which is an extension of the matrix, tensor SVD, which is an extension of matrix SVD to a 3-dimensional tensor. to third order tensor, to third order tensor. You know, this kind of TSVD was studied by Kummer and Martin. So they propose a new point of view of tensor, that is to view a tensor as a matrix, of tubes in the third dimension. So this is a really useful tool to study tensor decomposition. That is, you can see the tensor SVD is given by x equal to u, and this star is a T product. T product is a very beautiful algebraic structure on tensor. So x can be decomposed as u times sigma times v transpose, and u and v are orthogonal tensors. Sigma is a diagonal tensor. We can see this is a picture. This is a picture to view what is a tensor SVD. And this method is very practical because it not only processes the form of matrix SVD, but it's also also preserve the Laurent structure, when it transformed to the Fourier-Dauman. Now, by using this kind of tensor SVD, it is not hard to study such a low-rank approximation of tensors. This is our objective function. We want to minimize this. We want to minimize this Frobenius norm. And this part, tau is a Lagrange multiplier, and this part is a penalty. That is to find a low-rank tensor Z which can approximate tensor X. And in our research, to approximate, it is well known that the rank of a tensor is NP hard to compute. So we can use some functions to approximate the rank of Z. In our research, we use non-convex rank approximation. For example, Shattan-P quasi-norm and log determinant. So before people use the nuclear norm to approximate the rank function. However, it has long been noticed that there's a gap between the nuclear norm and the rank function. So this is the reason why we want to use non-convex rank approximations. So Fazel and Boyd, they observed that because the nuclear norm is to take the summation of the singular values, and the rank is the number of singular values. So there's a gap between nuclear norm and the rank. So we try to use the non-convex approximation of tensor rank other than the tensor nuclear norm. So from this picture, we can say here m is the singular value, and if we consider only one element, that means the rank is always 1 if x is not 0. Now, if we want to use a linear function to approximate the rank of a tensor, then when the singular value is very big, so the gap is also very big. There will be a big gap, between the non-nuclear norm and the rank. So we try to use non-convex function to shrink less the singular value to shrink less. That means you can see when m become bigger, the gap between this non-convex function and the rank is not as big as the nuclear norm. So that's the reason of why we introduce non-convex functions. So it is not easy to solve. It is not hard to solve the non-convex tensor rank minimization problem. So because we can transform this objective function into the Fourier domain, and then we can solve this equation, in Fourier domain. And then we take the inverse Fourier transform. We can get the solution to the original optimization problem. Now, it is very natural to extend robust PCA from recovering a low rank matrix to recover a low rank tensor. So that is our objective function. And if we use a non-convex rank approximation of the rank of L, we can use ADMM algorithm to solve the Lagrange function, to solve this optimization problem. So this is our experimental results. You can see this is an original tensor, original image which can be stored as a tensor. And this is the corrupted image. And we can use the tensor robust PCA to recover the low rank structure of this corrupted image like this. So you can see the result is very nice. And you can see the result is very good. So in multi-view clustering, we can store those images into a tensor. You can see here, we can store those facial image in a tensor. And then we can store the image as a tensor, and then we can do the self-representation learning to find a self-impressive tensor which satisfies x equal to xz. So this is a well-known condition for subspace clustering. And if Z is low rank and has a block diagonal structure, so we can use the geometry of Z to construct such a multi-view clustering results to do the multi-view subspace clustering. You can see our result is also very good. So, and in the future, we will study more applications of tensor, such as background and foreground separation in video, and we will develop more and more theoretical foundations of non-convex formulation. Thank you.